All right, exercise 2H, simultaneous equations. So at bare minimum, when you're walking into, and you've done your holiday homework as well, is that you should already know simultaneous equations, how to do. There's two key methods that you would have learned. First one starting with S, what was it called again? Substitution. So you need to know how to do substitution method. And then you also have elimination. You'll be using these techniques pretty soon as well. So you need to know how to do it by hand and also by CAS. Now, in this exercise, it's not about you knowing how to do that, because that was in chapter 1 already. What they want you to do is to understand what is simultaneous equations. When you do simultaneous equations, especially of two linear equations, so if they gave you something like 3x plus y equals 1, and another one is 2x minus 5y equals 8, right? And then you use your simultaneous techniques to solve, what are you really doing? Notice these are two linear equations. What you're actually doing is you're finding the point of intersection. Write that down. That's if I had time, I would actually describe why elimination and substitution works. It's actually because you're trying to find the point where they both cross at the same point. Okay, so two straight lines, when you solve for using substitution and elimination method, what you're solving for is x and y. You're actually solving for the point of intersection of two straight lines. But it doesn't have to be two straight lines. It could be a straight line in a quadratic equation. It could be a straight line in an exponential equation. So just knowing that when you equate two equations, you're finding point of intersection. Okay? Now, thanks team. In this exercise, they want you to be familiar with three key words. No solution, unique solution, and infinite solution. What does this mean? Exercise 2H wants you to understand if you've got two straight lines, the only way you don't have a solution, meaning no intersection, is if you have two straight lines that are parallel. That's the only way that they're never going to intersect. Unique solution just means you have one answer. There's only one intersection, because two straight lines, there's only one point it's going to intersect. So hence, you can only have one line, and the other line has to have a different gradient for it to have one point of intersection. What do you think infinite solution would mean then? How is it possible two straight lines will intersect infinitely? Molly? Same line. There's only if you had one line that's like this, and then you had the second line, which is exactly the same line as well. That's the only way you intersect infinitely. So on a logical basis, you've got three scenarios that could occur, and we know that the equation of a straight line is y equals mx plus c. Now you've learned from parallels and perpendicular lines, when it's parallel, what do we know about m and c? What can we say? So for two straight lines to be parallel, what do I have to make sure? Gradient is equal. That's all you need to make sure. So as long as m1 equals m2, as long as that's good, all good. That will be parallel. But what do I have to make sure about c so that it is not going to be infinite solution? Good. You can't have the two y-intercepts C1 and C2 equal, because if both m and c are the same, then it's the same equation. They both have the same gradient and they both have the same y-intercept. Well, of course, you're sketching the same equation, so then it becomes infinite solution. So here, put a cross. C1 cannot equal to C2, but M1 and M2 must equal. The gradients have to be equal for it to be parallel. So infinite solution would mean M1 and M2 must equal, and C1 and C2 must equal. If both M's and C's are the same, well, you have the same equation, so of course you get the same line. Then you go back to unique solution. How do you make sure that you're always going to get one intersection? It's what I do in my year 8s, and they're always like, oh, how did you know? How did you solve it? I'm like, guess the number, I'll tell you if it intersects or not. And I'll give them another equation, I'm like, this will never intersect. They're like, wow, how'd you know? There's only one theory that I'm doing, so I'll type that on Desmos for them to see. How do you make sure that they will definitely intersect? Molly? Yeah, that's it. That's all you need to make sure. M1 and M2, make sure they don't equal. Because if the gradients are different, think about a table. You have to keep the slants exactly the same. That's the only way they never touch each other eventually, or like it curves. But if you keep even 1 degree off, it will eventually taper in. That's why as long as the gradients are different, it will always intersect. So this is what I do with my year 8s. And they're like, oh my God, so good. I go to Desmos. Where's Desmos? I usually have it already up here. And I go to Desmos, which is further down or down here. Desmos, and this is what I do to them, just to make it scary. Instead of typing y equals, I do like 3x minus 1 3 minus y equals 5, right? And I don't care about what crazy numbers. I can type fractions and all that. And then I do this. I say, all right, I want to type another line, okay? And I want you to tell me, is it going to intersect? And all I do, I just make sure that number in front of x, which is the gradient, it's not the same. Just make sure it's not 3x, right? So I just do, 2x minus 2y on 3 equals to 5 on 6 on 7. I don't know. I just make it up. And I'm like, promise you, this will never intersect. Let's have a look. And I zoom out. And I'm like, oh. And I'm like, let's go all the way up. And I'm like, let's zoom in. And I'm like, it just never intersects. Like, how do I know? And then I'm like, oh man, does that look parallel? But if you actually keep going and going, at some point, there is a point. Obviously, I made it up. Usually I make it so that you can actually zoom in and you'll see where the intersection is. But these two should intersect at a point. But at this point, it feels parallel. And they're like, oh, it's parallel. I'm like, everyone's sure it's parallel? And then I go look for it. And we keep going. And then eventually find the intersection because you can see it's starting to taper in. I can't be bothered finding it now. I don't know where it is. I have to solve it. But that's an example of how you know a theory really well. And you can solve where the intersection is for this equation if you really wanted to. Yeah? So, here we go. We go back to your exercise 2H. If you understood those 3 things I just described, that's all they want you to know. That's the essence of 2H. The questions that you're going to work with, you're just going to be comparing these, and you're going to learn to prove it. So here, for a unique solution, as long as the gradients are different, actually doesn't matter if the y-intercept's the same. Who cares about the y-intercept? So you can keep C1 equals C2, or C1 doesn't equal to C2, doesn't matter. You'll always have an intersection as long as the gradient is the same. Okay? All right. So, and this is an example, 2x minus 4. I usually then type another equation with the same gradient, different y-intercept, and you'll see that it will be parallel or will not be parallel. So if I go back to Desmos, let's do it. As an example, y equals to 2x minus 4. This is what it looks like. That's 2x minus 4. So if I type another equation, if I keep the same gradient, so 2x, you notice it's already parallel. Doesn't matter what y-intercept is. If I do 1, it's there. 2, it's there. It's still parallel. But as soon as I do minus 4, it's the same line, so infinite solutions. If I go back to plus 4, the only way to make it intersect, change the gradient. If I made this 12, here's my intersection. I chose 12 because I made sure the gradient's very steep. So it's obvious to see. Okay? So that's all you're really trying to learn in 2H. The questions they give you, I'm going to show you. This is all they want you to do. You're going to look at these questions here, for example. Remember 2F, how I said family of lines? You don't know what M is. You know the y-intercept is 6. Now they're saying, for what values of M does the line not intersect this line? So if I did A with you, you got y equals 4x minus 5. And the other line is y equals to mx plus 6. They both have different y-intercepts. But if I don't want them to intersect, what do I have to make sure? So not intersecting means they're parallel. They're not intersecting means they're parallel. They're running together. How do I make sure that these 2 equations are going to be parallel? Yeah. M has to be 4. That's all I do. See what I mean? So that means if I just say this answer for part A was that M1 had to equal to 4 to be parallel. That's it. See, if you understand the theory, answering the question is easier. If you don't understand the theory and you look at this question, it looks scary because there's the M. right? So I want you to understand the theory. There's only three things that you know. No intersection, one intersection, and then infinite intersections. Okay, you can try B as well. B is the same thing. For what values of M, same thing to intersect. So if you want it to intersect, how do you write the answer for this one? If you want this line to intersect with that line, what should it be? Okay, so this is where it's important. In year 12, if you write anything but 4, but you write it like this, you'll fail or you lose a mark. Okay, because you're not saying anything. You're not saying it can be anything. You're just saying it can't be 4. So I'm like, so what can it be? Right, so you need to say M can be anything except 4. Later on, you'll learn the notation for it. You would say something like M is an element of all real values except 4. Now, I haven't taught you set notations yet, but that's what it means. That means M is a part of R means any number possible. Backslash means except 4. That's the proper way of doing it. Sorry. No, you don't write it. Well, at the moment, you guys will be doing that at year 11 until I teach you set notations. But you can write M equals any value except 4. For now. As long as I understand that you understand what you're doing, right? But this is the proper way. So you'll find in year 12, they'll never write this. They'll write this. They'll write the set notation the same. M can be any number except 4. And then you have intersection. So you can see I'm not really doing a lot of maths here. I'm doing a conceptual maths. That's what methods is. It's about hypothetical thinking. And your last one, if the line y equals mx plus 6, which is the same line, and y is at the point 515, find the value of m. That goes back to exercise 2f. So if they have to intersect at 515, that means that both equations, when you sub 5 for x, the y should be 15. They're saying, what should m be? Well, that's very easy. It sounds hard, but it wasn't that hard. You got y equals mx plus 6, and you've got y equals 4x minus 5. If they both intersect at 515, well, that means you sub the point in both, it should equal the same. So all you have to do is you're saying 5 can go here, and 15 has to go there. 5 can go here, and 15 can go there, because they both intersect the same point. So that's true. Who cares what that is? No one needs to waste their time on that. You're trying to find m. So just solve this. So all you're doing is, what is 15 equal to m times 5 plus 6? It's basic year 7 equation. Subtract 6 on both sides. 9 equals to 5m. M must equal to 9 on 5. So the question looked hard, but as I'm going through it, I hope that you're seeing it's a very conceptual idea. It's a very straightforward idea. Yeah? I'm going to pause the video there because the next exercise, I think that's question 6. I already got a video on that if you want to watch, but have a go with the theory. It's about the theory, and then you apply your knowledge. As you go through the questions, they just get a bit more tricky with algebra, but the theory is the same. Okay? I'm going to stop.